So in this video, we're going to talk about independent events. So just to motivate the topic, let's say we have a fair coin and it's flipped 10 times. And for some reason, every single time you flip that coin, it comes up heads. Well, on the 11th flip, what's the probability that the heads comes up again? Well, the coin doesn't remember anything. So the probability that the head comes up on any given flip is 1/2. So the first 10 flips of that coin have absolutely no effect on the 11th flip. So the probability is still 1/2. So this is what we mean by being independent. So since the first 10 flips gives us no information about the probability on the 11th flip, we say that the events, heads comes up on the first 10 flips and heads comes up on the 11th flip, are independent events. So again, the idea here is that having that additional information has zero effect on the probability of the other independent event. So here's the formal definition. A and B are independent if the probability of A given B is the same thing as the probability of A, or likewise, the probability of B given A is the same thing as the probability of B. This is assuming the probability of A, and this is a typo, this should say probability of B are non-zero. In other words, knowing the event B occurred has absolutely no effect on whether or not A occurred, and vice versa. So, if looking back at our conditional probability formula, remember we had the probability of A intersect B was the same thing as the probability of A times the probability of B given A. Well, if the probability of B given A is the same thing as B, probability of B, I mean, because they're independent, we can write the probability of A intersect B as just the product of the probabilities of A and B. Now, in this case, this formula works no matter if probability of A or probability of B is 0. That's because certainly if either of them is 0, we get 0 on the right-hand side. If the probability of A or B is 0, that means there's nothing in the intersection because there's nothing in A or there's nothing in B. All right, so there's a theorem that goes along with independent events. It says that if A and B are independent, then so are A complement and B, A and B complement, and A complement and B complement. So let's do one of these proofs. It's not too bad to do. So we know from the conditional probability formula that if I do the probability of A intersect B, A complement intersect B, that's the same thing as the probability of B times the probability of A complement given B. I don't know why that's not advancing to the next slide. Probability of B then, we can replace the conditional probability with 1 minus the conditional probability of A given B. That's because the conditional probability forms, or we know that these are either or in the sense of conditional probability, either this happens or this happens. We know that A and B are independent, so the probability of A given B is just the probability of A. This is using the independence part. And then this last part here is just 1 minus the probability of A is the same thing as the probability of A complement. And so since we've shown that, since we've shown that the probability of the intersection is the product of the probabilities, the two events are independent of each other. Sometimes we're interested in the independence of 3 events. So we refer to those as being mutually independent. So to be mutually independent, that means that they're pairwise independent, meaning that A and B are independent, A and C are independent, B and C are independent. But we also need that the probability of the intersection of all 3 also breaks up as a product. Okay. It's possible to be pairwise independent but not have this last condition met. So let's say as an example here, just using that new concept, let's say we have the mutually independent events A, B, and C. Given some information about their probabilities, let's see if we can figure out the probability of this union. All right, so from information that we've talked about before, a theorem we've had before, the probability of this union can be broken up in this fashion. Probabilities of the individual pieces, and then subtract off the individual intersections, and then add back the triple intersection. They're mutually independent, so that means I can break up all of these intersections as products of probabilities. And now I know each of these pieces because now I have everything in terms of probability of A, probability of B, and probability of C. Probability of A complement, in this case, is the same as probability of A. It'll be a half. Probability of B complement will be 0.4. And probability of C is given to us as 0.1. So this is just plugging in all of those numbers, and we simplify to get 0.73. Let's do another example here. A little bit more of an applied problem rather than just using the formulas. We've got an insurance company paying hospital claims in this example. We've got claims that include either emergency room charges or operating room charges is 85% of the total claims. Claims that do not include emergency room charges is 25% of the total number of claims. And emergency room charges is independent of operating room charges. So let's calculate the probability that a submitted claim includes operating room charges. All right, so we know that we're given the number of claims that include operating room or emergency room is 85%. So we're going to start off with the probability of that union because that's a piece of information that we're given, emergency room or operating room. We know from a theorem that we've had before that we can break up the probability of the union in this fashion. All right, operating room charges, we don't know. That's what we're looking for, right? It's asking us to calculate the probability of operating room charges. So there's nothing I can plug in there. We are given something about emergency room charges. We know that claims that do not include emergency room charges is 25%. So we can rewrite the probability of having emergency room charges in terms of its complement. So that's where this 1 minus probability of E complement comes from. And we know that operating room charges and emergency room charges are independent of one another, so we can break that up as a product. And now we can plug in the pieces that we know. We know that the probability of E complement here is 0.25, so the probability of E is 0.75. So on the right-hand side, I can plug in both occurrences of this probability of E, I know is 0.75, and I know the probability of the union is 0.85. Both of those pieces are given to us. And now I have an algebra problem to solve. I can move the 0.75 to the other side and combine these two terms together and get 0.25 times the probability of the operating room charges. And then simplify and I get 2/5. So the probability that a claim submitted to the insurance company includes operating room charges, is 2/5 in this case. We'll do more examples of using independent events in class, but notice it's a lot like what we've already done with conditional probability. Basically, the independence is still just an and probability. You've got one thing and the next thing, like with this intersection here. That's where we're using the independence. We've already done and probabilities. We know we need to multiply. In the conditional probability stuff, we just had to worry about changing the sample space. If they're independent, we don't have to change the sample space. We just have to multiply the probabilities. So like I said, we'll do more examples of like these in class on Monday.